Second law of motion. And before the second law of motion, what it tells us, the second law of motion, it gives us a quantitative approach towards motion, force. Quantitative definition. So quantitative definition of motion is given by the second law of motion. And what it tells, before that, we have another statement, that's we have to understand another term, that's momentum. Momentum is another term which is used to describe the amount of motion contained in an object. Okay, so here we talk of momentum. Momentum is a physical quantity which measures the amount of motion content in an object. Okay. So it measures the amount of motion content So we see what is momentum. First we understand what is momentum and then we'll apply this knowledge of momentum. I just saw that in the second law of motion we have to understand what is momentum. And what is momentum? It is the amount of motion content in an object. What is the amount of motion? And the amount of motion content in an object, it depends on two factors. The amount of motion, that is momentum, it depends on two factors. It is directly proportional or it is dependent on mass and it is dependent on velocity. So momentum is, you can say momentum is equal to the product of mass and velocity. We can directly write momentum as the product of mass and velocity. However, at many times you will directly find the definition of momentum as the product of mass and velocity. Okay. So what is momentum? It is the product of mass and velocity. So it depends on mass and it depends on velocity. As we can see here, it is the product of a scalar and a vector. Therefore, momentum, it is a vector quantity denoted by the symbol P. So P equals mv. P is a vector quantity or momentum is a vector quantity. This is a small letter p. It's a vector quantity. So what are the factors on which this momentum depends? It depends on mass, it depends on velocity, and its SI unit. SI unit of momentum. Pranaya, what would be the SI unit of momentum?
Because it's the product of mass and velocity, it would be kg meter per second square. No, second.
Per second, it would be kg meter per second. So the SI unit of momentum is kg meter per second. This is what we call as the momentum. Now, if you really want to understand what we are saying, Siddharth, where is your attention, Siddharth?
Yes, sir. I'm actually watching, sir. Actually, my computer is turning on. I'm actually on phone right now. I'm joining from there.
Okay. So let's see. So SI unit is kg meter per second. And if you want to understand what is momentum, so let us consider two objects. Let us consider two balls. Okay. So let us consider two balls. This is a cork ball. I hope you have seen, all of you must have seen that cricket cork ball. And this is a Costco ball that we are going to see. If you throw both the ball with same velocity, let us say both the balls, they have the same velocity v. All of them, they have the same velocity v. So which one would require a greater force to come to rest?
The
The
one
ball with the
with
more
mass.
mass.
Which require more? Rikshit? Rikshit? Abhinav?
Yes, sir.
Yeah, which would require a greater amount of force to stop?
The Costco ball because it has more mass.
Okay, which has more mass, Costco ball or the cork ball?
Costco
Huh?
ball.
Costco ball. Do you see that Costco ball is a tennis ball? That's a tennis ball that we use. Let's call it as a tennis ball.
Sir,
Yeah,
it's a cork ball.
yeah, it's the cork ball. The cork ball is more heavier that we
Yes,
use
sir.
in the cricket stadiums.
Sir,
So that
by
is a
the way,
cork
can you
ball
hear
which is
me?
more heavier. It is about 3 to 4 times heavier than a Costco ball. Okay,
Sir, can you
so
hear me?
yeah,
Can you hear me, sir?
who is this speaking? I think
Sir, Rikshit, sir.
Rikshit. Yeah, Rikshit, you are audible, but your voice level is too low.
Okay, sir. 1 minute.
Okay, just your voice level is low. So cork ball will require a greater amount of force as it has greater amount of motion contained in it, which we measure by the amount of momentum that it has. Okay. So we can say that the momentum of cork ball is more and the momentum of Costco ball or the tennis ball is less. So in the similar way, there are various situations where we can analyze about the momentum. In the same way, you can consider, let us say, a car and a bicycle moving with same speed. Okay. So then which would require a greater amount of force to stop? A car? The car would require a greater amount of force to stop. Yeah.
Sir, car and
A car and a bicycle. Both are moving with same speed. So a
yes,
bicycle can be applied by applying a small amount of force.
small amount of force, sir.
Okay. But the car requires a larger amount of force. Okay. As there is a large change of momentum in the case of car, but for the bicycle, there is a small change of momentum. So I hope we have understood that momentum, it measures the amount of motion content of an object and it depends on both mass and velocity. Okay. The momentum of an object, it depends on mass and velocity. Okay. So you can calculate the momentum of any object as the product of mass and velocity. Now let us calculate this small question. Okay. So a ball of mass 200 gram is moving with 90 kilometer per hour. Okay, find its momentum. Just find its momentum. What would be the momentum of the ball? Abhinav, what's the answer? Abhinav,
Wait, sir, I'm still doing.
okay. Turn on the camera. You should turn it off.
Sir, is it 5 kg meter per second?
You are saying 5 kg meter per second. Okay. So let's check others' answer also. Okay. So what we need to do first, we need to convert this 90 kilometer per hour to meter per second. Okay. So the shortcut way to convert this 90 kilometer per hour, we need to multiply this 90 by 5 by 18.
25.
So it is 25 meter per second. And the mass is 200 gram, which is equal to 0.2 kilogram.
Sir, can you hear me now?
Yeah, now you are audible, Richard.
Okay, sir.
Okay. So you will compute your momentum, which will be product of mass and velocity. It's 0.2 multiplied 25. Okay. So you get a 5 kg meter per second. So who all had got this answer? I think Pranaya had got this answer. Siddhant got this answer. Anyone else who got the same answer?
Even I got the same answer. So.
Okay. So that's good. All of you. Kaushik, did you get the answer?
Yes, sir.
Okay. So this was a simple concept of momentum. Now we define what's force, what we call as the force. So a force, here we are going to give the qualitative measurement of force. That means how we can measure the force. Okay. So force is measured, it is measured as the rate of change of momentum. We say force, it is directly proportional to rate of change of momentum. So force, it is directly proportional to the rate of change of momentum. Okay. So how we write? The force acting on an object or the net force acting on an object is directly proportional to the rate of change of momentum. This is called as your second law of motion. So we also call it as the second law of motion, that net force acting on an object is directly proportional okay.
Wait, sir, in the P equals MV, what does P stand for?
Yeah,
I forgot that part on me. What does the P stand for?
P stands for momentum. That's a small letter
Then,
P, it stands for momentum.
okay. Then what does the M stand for?
Mass.
Right? Mass.
Okay. So this is the statement of your second law, that net force acting on an object is directly proportional to the rate of change of momentum with respect to time. We can say that force F is directly proportional to rate of change of momentum. So we write it for you, I write it as rate of change of momentum. So it is rate of change of momentum with respect to time or per unit time. Rate of change of momentum with respect to time. Okay, so how fast the momentum is changing, that determines the rate. We can write it like this, that F is proportional to, we write the symbol delta P divided by delta T. Delta P, it means change of momentum. It means change of momentum, and delta T is the change of time. So what is force? Force acting on an object is directly proportional to the rate of change of momentum. Okay. So I hope just delta means the change and P means momentum. So change of momentum with respect to change of time. I hope you have understood. So change of momentum, it can be written like, so change of momentum F proportional to, it can be written like uh, final momentum. Whatever change we want to measure, we can measure it as final minus initial. And the change, let the change of time be t. Whatever time has changed, let that be denoted by t. Okay. So final momentum minus initial momentum. Whatever change we measure, what is its final value, then what is its initial value. So subtract the initial value from the final value, then you get your moment change. So similarly, we can write here force proportional to final momentum. So we can write, since momentum is denoted as P equals m into v. Okay. So momentum is denoted as mass into velocity. Now mass is measured in kilogram and it's invariable. Mass does not vary. Okay. What varies over here is velocity. Okay. So if you have a mass, let's say I have a mass m. Okay. A mass m which was initially moving with some velocity u, and after some time this mass m, it was found to be moving with some velocity v. So mass is the same. What has changed its velocity. So if I want to calculate my final velocity,
Yes, sir.
final momentum, sorry. Final momentum will be denoted by mass m into v, and initial momentum will be given by m times u. Okay, as u represents the initial velocity. So I can write here force proportional to mv minus mu over t. Since mass is common, we take out mass as common and you get v minus u over t. So this quantity, Varshita, what is this v minus u over t?
Sorry, sir.
What is this v minus u over t? What do we call this quantity as?
Acceleration.
Yeah, Varshita?
First known as acceleration.
Acceleration. So this v minus u over t, it is acceleration, and hence we can write as force proportional to mass times acceleration. Okay. The proportionality constant, if we remove this proportionality and introduce here an equality sign, so I can write here force equal to a constant multiply mass times acceleration. The value of this constant is calculated to be 1. It is taken as 1. So force is equal, I can say that force is equals mass times acceleration. Okay. But this we have considered, this we have taken out considering mass to be an invariable quantity, that the mass of the quantity is not varying. Okay. Otherwise, you can use this one also. Whenever required, you can always use the formula this. You can say that force is equal to change of momentum per unit time, mv minus mu over t, as the value of constant of proportionality is 1. So all of them, they hold good. So the Newton's second law of motion, it gives us that force acting on an object is mass times acceleration. And from here, we can define the unit of force. Okay. So force, it is measured in Newton. We take here SI unit of force as Newton. SI unit is Newton. And it is equivalent to kilogram meter per second square, or kg ms minus 2. This is the SI unit of force. Okay. As mass will be measured in kilogram and acceleration is measured in meter per second square. Okay. This is also called Newton, written with small capital N. 1 Newton. So when do we say that a force of 1 Newton acts? Can anyone define what is 1 Newton?
The force required to move an object of 1 kilogram
Hmm.
with an acceleration of 1 meter per second square.
Yeah, if the amount of force required by an object of mass 1 kilogram to attain an acceleration of 1 meter per second square is called 1 Newton. So that is 1 Newton of force. Then the CGS units, we also have the CGS units of this force. In the CGS units, we will be measuring this mass in gram. So over there, we will measure this mass in gram and acceleration in centimeter per second square. So this gives us another unit, gram centimeter per second square. It is also called dyne. Aman and Abhinav. Abhinav, is there any problem? Aman? Okay. So SI unit is Newton, and for the CGS unit, it is dyne. Okay. Now, can we obtain an equivalence that how many Newton will be equal to 1 dyne? Or let's say 1 Newton is equal to how many dyne? We want to find out this. So 1 Newton is how many dyne? So we want to
10
convert
to the
from,
power of 5.
it is equal to 10 to the power 5. Okay. You can convert as 1 Newton is kilogram meter per second square. If you convert this, kilogram to gram is 10 to the power 3. Meter to centimeter is 10 to the power 2 centimeter. And per second square, it remains the same. So you have 10 to the power 5 gram centimeter per second square. Okay, so let's do another small question. Shall we do a question? Okay, let's say hmm, just wait, second law of motion, and here this is a question. Just try this example 9.1. Okay. So I'm giving you this 9.1. Let's try to solve this. Okay. So a constant force on an object of mass 5 kilogram for a duration of 2 seconds. Okay.
Sir, I'll be right back.
Yeah.
I'll come back like in 1 minute.
Okay. So the question is, a constant force act on an object of mass 5 kilogram. Here it's given mass as 5 kilogram. for a duration of 2 seconds. The time which it represents is 2 seconds. It increases the object's velocity from 3 meter per second to 7 meter per second. So the initial velocity is given as 3 meter per second and final velocity is given as 7 meter per second. Find the magnitude of the force applied. You have to calculate the amount of force.
Sir, is it
Okay.
10 newtons?
Yeah. Varshita, what's your answer? Aman?
Sir, 10.
Okay. Aman, your answer is 10?
Yes, sir.
So
Okay.
it's definitely 10.
Okay. So we obtain the answer 10. Either you can first calculate the acceleration, which is v minus u by t. And this is equals to 4 by 2, which is 2 meter per second square. Then you calculate your force, which is mass times acceleration. 5 times 2, that is 10. Now find the magnitude of the force applied. Now if the force was applied for a duration of 5 seconds, what would be the final velocity of the object? So all of you calculate this part now. Now if the force was applied for a duration of 5 seconds, the same force was applied for 5 seconds.
Sir, 13.
13. You are saying final velocity would be 13.
Sir, no. Wait 1 minute. No.
Sir, he's right, actually.
You are right. Final velocity will be 13 since we have
Sir,
obtained.
I just checked the questionnaire and just told the answer. I didn't do the rough work.
Okay. See, acceleration is 2 meter per second square.
So yes, sir, it's 30.
Okay. Initial velocity is 3, so you can calculate the final velocity v equals u plus at. Okay. So u is 3 plus 2 into 5. This is a 13 meter per second. Okay, let's see the next question. Okay. So this one, a motor car. Let's see. This one. A motor car is moving with a velocity of 108 km per hour. It takes 4 seconds to stop after the brakes are applied. Calculate the force exerted by the brakes on the motor car of its mass. Calculate out this question. Abhinav, what the answer?
I'm doing survey.
Okay.
So the acceleration is negative, right?
Yeah, acceleration will be negative.
So the force obtained will also be negative.
Yeah, force will also be negative. So we have
7,000. Sorry, minus 7,500.
minus 7,000.
27,000.
7,500, sir.
7,500. This is initial velocity 108 km per hour. Converting it to meter per second, it's 30 meter per second. Okay. Then calculate your acceleration, which is 0 minus 30 divided by 4. So it's
That was minus 30 by 4. Minus 30.
negative 15 by 2, which is negative 7.5 meter per second square. Force would be 1000 multiplied over minus 7.5. So it's 7,000 negative of 7,500 Newton. So let's see this one. The velocity time graph. You can see the velocity time graph of a ball of mass 20 gram moving along a straight line on a long table is given in figure this. How much force does the table exert on the ball to bring it to rest? See here the velocity is in centimeter per second.
Minus 40 grams per centimeter square.
Minus 40 gram per centimeter square. Okay, so you're saying minus 49.
Sir?
Okay, if you see your acceleration, if you are calculating in the same units which are given, so it will be 20 minus 0. So 0 minus 20, it will be final minus initial. So final is 0 minus initial, which is 20, and divide by time, which is 10. So it's minus 10 centimeter per second square. Oh, sorry, minus 2. You get minus 2 centimeter per second square. Then force is mass times acceleration, which is 20 multiply minus 2. This is minus 40 gram centimeter per second square, which you can also write as minus 40 time. If you want to write it the answer in Newton, you can just write minus 40 multiply 10 to the power 5. Okay. Now we move to the third law of motion. Okay, Aman, what does the third law state?
Sir, every action has an equal and opposite reaction.
Okay. For every action, there is an equal opposite reaction. So this is the statement of the third law, that for every action there is an equal and opposite reaction. So first we'll understand this concept. What does it mean? For every action, there is an equal and opposite reaction. So this is our statement of third law of motion. Third law. So according to the third law of motion, every action there is an equal and opposite reaction. Or you also can say from here that forces always occur in pair. There will not be just a single force. There will be two forces. So forces always occur in pair. We will try to understand this and then apply its meaning. For example, consider a wall over here. This is a wall. And suppose you are standing over here on roller skates. You are wearing those roller skates and you are standing on these roller skates over here. Okay, so let's make you standing to be here. And if you push this wall, so what is going to happen? Once you are pushing the wall,
The person falls down.
the person falls down. Won't these
We
roller
get
skates?
pushed back.
He will be pushed back. Okay. He will be pushed back and he falls or he balances his body, that's his problem. But he will be pushed in the backward direction. Okay. So what was his action? His action was pushing the wall. And as a result, he obtained a reaction. So now see, what is point to be understood here? The man applies the force on the wall. Right? So we see here, man applies force on the wall. So how many forces are acting on the wall? That's the force of man. Okay. So the man's push is acting on the wall and the wall is also pushing this man. So this force is being acted by the wall on the man. So man is getting a reaction force over here. Now the words action and reaction, it does not mean that only the push of the man is action and the push of the wall is reaction. Okay, you can call any of them to be the action force and any of them to be the reaction force. Any of these forces, they can be called as action. Even the push of the wall can be called as action and the push of the man can be called as a reaction. As there is no time delay. There is no delay that first man pushes, okay, then after some time he gets the reaction. No, it's an instantaneous same time reaction. Okay. Let's understand this in another way. Okay. Suppose if you have a block and you tie this block with a thread. Okay, we tie this block with a thread and let's try to pull this. Let us stand over here and try to pull this. So we are pulling this. We are pulling this along this direction. Okay, this is our apply of force. We apply over here. So it says that if we apply action and reaction, it says that I am applying a force on this block. Okay, so I am pulling this block. And there is another force which is acting. This block is also pulling me in the backward direction. Okay, so do you agree that the block also pulls me in the backward direction? Yes, everyone, do you agree that if I'm pulling the block, so the block also pulls me?
No.
No.
No, sir.
Why?
Sir,
Okay.
because you
Okay. Consider this surface to be frictionless. Let this surface to be made up of ice. Okay. and you are pulling this. So the block will also move towards this side, and you will also move towards the block. Will it happen or not? It will happen that the block will move towards you, and you will also move towards the block. Okay. So it's correct to say that the block also pulls us. The amount of action is always equal and opposite to the reaction. Both the forces, they are equal and opposite. Okay. So if I am pulling the block is pulling me also. Everywhere it is correct. Action and reaction, they always exist in pair. We will see this in various other examples, like I think you might have heard this one a number of times. A rocket moving up. So when a rocket moves up, how is the rocket moving? Who is applying the force on the rocket? Yeah. See,
So the gases push the rocket
yeah, the
as a reaction.
gases are moving out of the rocket, and to move out of the rocket, the gases must push the rocket. Hence, the gases are moving out, and they are pushing the rocket in the upward direction. Okay, so this is also your action and reaction. The movement of gases in the downward direction, this is your action, and the movement of rocket in the upward direction, this is your reaction. You must have tried these activities a number of times. If you inflate a balloon and just leave it, inflate a balloon and leave it, so what will happen? All the gases, all the air which is inside it, it will try to move out. All the air from the balloon, it will move out, and hence an upward force will be created. Therefore, balloon will move in the opposite direction of those gases. So the balloon also moves in the opposite direction of the gases. You see here, here another example, a man jumping from his boat. So when the man jumps off the boat, he is pushing the boat in the backward direction. Hence, he is gaining a reaction in the forward direction. Therefore, the man is able to move in the forward direction. In the similar way, we see a number of action and reaction contributions every day. Like when we are walking, so our walk is also action and reaction. Okay. When we are walking, then also there is an action force which is acting in the up. By the action force, we are pushing the ground, and it is the ground which provides us the reaction. So while walking also, we are using action and reaction. Okay, so let's see a few questions, and then we will move to conservation of momentum. We will see conservation of momentum. Okay, let's try to do this question. We have to do question 6 and 7. Let's try to solve question 6 and 7. Okay, so all of you solve question 6. So you have a stone. A stone is being thrown over here on the frozen surface of a lake. So on this frozen surface of a lake, we are throwing a stone with initial velocity of 20 meters per second. Then this ball comes to a rest, or the stone comes to a rest after traveling a distance of 50 meters. So it travels a total distance of 50 meters. This is the distance between them. Meter. So its final velocity is 0. It finally comes to a stop. Right? And its mass is given as 1 kilogram. So again, the same thing, since you want to calculate your first force must be equals to mass times acceleration. So we know the mass, we just need to calculate the acceleration. Okay. Siddhant, have you got the answer?
No, sir, just 1 second, sir.
And Chavan Kaushik, have you got answer?
No, sir.
Okay. So do you know how to solve it out?
Yes, sir. Sir, first we have to use that equation of motion. Then
Mhm.
we'll get the acceleration, and then by using the acceleration, we have to find the force applied.
Okay. Varshita, what happened? You didn't get the answer?
Sir, I found the answer, sir. 4 newtons.
Okay.
It's -4.
2 times acceleration into displacement is 50. Okay, so it's minus 400 divided by 100. So acceleration is -4. Acceleration is -4, and your force is 1 into -4. So that is also -4 Newton. Okay. So everyone got this answer, -4?
Yes, sir.
Okay. Now try the next one. Do I need to just read and I'm explaining this? Then you can start solving. Orosmith? Orosmith?
Yes, sir.
You are not telling any answers. And even Aman,
Sir, I'll on my camera after 2 minutes.
okay. I'm not getting answers from you people, that's why. Okay. So you have a 8,000 kilogram engine pulls a train of 5 wagons, each of 2,000 kilograms, along a horizontal track. If the engine exerts a force of 40,000 Newton and the track offers a friction of 5,000 Newton, then calculate the net accelerating force and the net acceleration of the train. Okay, so I think Aman shall explain this. Aman, will you try to explain the problem? Aman? Do you have your engine? It's followed by some wagons. Okay, who will explain then? Pranaya?
Yes, sir. So basically there is this engine whose mass is 8,000 kgs. No. Like the engine pulls a train of 5 wagons, and each wagon is 2,000 kgs. So we have to multiply 2,000 into 5, which would be 10,000 kgs. And then like the mass of the engine is 8,000 kgs, and the force of the engine pulling the wagons would be 40,000 newtons. It's like the force applied by this is 40,000 newtons, and the frictional force is 5,000 newtons. And we're supposed to find first the net accelerating force, which would be the force of the engine minus the frictional force, which is 35,000 newtons. And then the acceleration of the train. We know that F is equals to ma, so the answer would come up to 1.944 meter per second square.
Okay. So I think Pranaya has calculated. Okay. So there are 5 wagons. Just like this, you have 5 wagons. Okay. Each weighing 2,000 kilograms. So total mass of the wagons, that's going to be 2,000 into 5, that's 10,000. So its total mass is 10,000 kilogram. And mass of engine is 8,000. Okay. So you have total mass, which is 18,000 kilogram. This is the total mass. Okay. Then the engine exerts a force of 40,000 Newton and the track offers a friction. So your net accelerating force you need to calculate, that is net force, will be given as a subtraction of this. It would be 40,000 minus 5,000, which is 35,000 is the net accelerating force. Then you can find out your acceleration, which is given by force by mass.
Wait,
So your force is
sir,
35,000, yes.
then what will be the final answer?
Final answer will be this 35 by 18. This
How
will be your
much?
x. Okay.
Like
So
1
that,
point something.
so this, yeah, that will be 1 point something. 1.8 or 9. You might be getting. Okay. So bye everyone. Good night.
Bye, sir.